Welcome back, everyone. I'm so glad you're joining me today for this explainer, which is proudly brought to you by Forge College. Now, if you've been following along with our Programming with Solana track, you'll remember that in our previous lesson, we covered configuring a basic entry point. We laid down the foundational wiring. Well, today, we are transitioning from that basic wiring to the actual beating heart of the logic. We're talking about the entry point structure in Rust. This is exactly where we define the absolute rules of engagement for our smart contracts.
Okay, let's dive into this. Here's our exact technical blueprint for today. 1. The Rust function signature. 2. Gatekeeping versus partying. 3. The Velvet Rope workflow. And 4. Shift change.
To really wrap your head around what an entry point is, I want you to hold on to a specific mental model as we go through this. Think of the entry point not just as a block of code, but as an incredibly strict, highly efficient bouncer standing right at the front door of a super exclusive club. This gatekeeper has one job and one job only: verify identity and check credentials. They're inspecting tickets, looking at IDs, checking the guest list. But, and this is absolutely vital, this bouncer never, ever walks behind the bar to pour the drinks themselves. They are purely a dispatcher. They process the arrival and send the guest to the right VIP room so the bartender, which is your business logic, can do the actual heavy lifting.
Number 1. The Rust function signature.
Keeping that bouncer metaphor in mind, let's look at the literal code boundary. This is the canonical Rust signature for a Solana program entry point. Now, if you're a bit newer to Rust, seeing pub-fn, process instruction, followed by a bunch of ampersands and brackets might look kind of intimidating at first glance, but I promise you, it's actually remarkably elegant. This right here is the contract boundary of your program. Every single invocation of your smart contract has to pass through this exact function shape. It takes exactly 3 inputs, no more no less, and produces a single output. You've got the program ID, the account slice, and the instruction data. Then it points to the output, a program result, which just tells the Solana runtime whether the transaction was a success or a failure.
Now, what's really interesting about this slide is how cleanly these technical data types map directly to our bouncer components. Look at the program ID. It's a pub key. In our metaphor, this is the badge. It establishes exactly which program is being invoked, which is crucial for verifying things like program-derived addresses or cross-program ownership. Next up, the accounts array. This is a slice of AccountInfo. Think of this as the credentials. It holds all the metadata, the balances, the owner, whether the account signed the transaction. Then we've got instruction data, coming in as an opaque slice of raw bytes, or a U8 array. This is the manifest, the actual binary payload carrying the specific action the user wants to perform. And finally, the return type, program result, is the outcome. Did the bouncer let them in, or did they get kicked to the curb with an error code?
Section 2. Gatekeeping versus partying.
You essentially have 2 ways to design your program, and I'm going to be honest with you, one of them is a complete nightmare. You could build a thick entry point. This is like a terrible, severely overloaded bouncer who checks your ID, then runs all the way behind the bar to mix your cocktail, runs back to the door, checks another ID, and tries to DJ at the exact same time. It handles business logic directly at the boundary. It's messy, it's monolithic, and it is incredibly hard to unit test because literally everything is tangled together. Or you can build a thin gatekeeper. This bouncer does nothing but parse the manifest, validate the credentials, and then immediately delegates the request to the specialized handler, the bartender. This gives you modular, highly testable code where your business logic doesn't have to sweat the low-level sanity checks.
So the crucial point here is this golden rule. Keep the entry boundary thin. I want you to practically etch this into your brain. The entry point should never contain long, winding paths of business logic. If you're out here calculating token yields or transferring LAN ports right inside your process instruction function, you're doing it wrong. Your entry point must be a strict, lean router that focuses entirely on gating and dispatching.
Moving to Section 3, the Velvet Rope workflow.
Let's move to and see how this actually builds out in practice. It creates a beautifully clean, 5-step deterministic pipeline. Every single request goes through these exact checkpoints in order. First, identity checks. Second, parse payload. Third, validate accounts. Fourth, dispatch. And fifth, map errors. It's a strictly linear workflow. By structuring your entry point this way, you're building a system that fails fast, saves precious compute energy, and perfectly isolates complexity. Let's drill down into each one.
Step 1 is all about immediate identity and sanity checks. The second a request hits the door, you do the bare minimum to make sure it isn't complete nonsense. You inspect the program ID to ensure any PDAs or cross-program ownership claims actually check out. You also quickly look at the length of the account slice. If your instruction absolutely requires 5 accounts to run and the user only passed in 3, you fail fast. You kick them out immediately. There is zero reason to waste the Solana runtime's compute energy trying to parse a payload if the basic required accounts aren't even there.
Step 2 is parsing the payload. Remember, that instruction data arrives as an opaque byte array. To our bouncer, this is basically just an illegible, hastily scribbled ticket. You absolutely cannot execute business logic safely on raw bytes, so we use a parser function to convert those raw bytes into a safe, strongly typed Rust enum or struct. This parser takes the messy outside world and translates it into a clean data structure that the rest of our Rust code understands perfectly. We pull out the opcode, we unpack the arguments, and we make the whole thing legible.
All right, step 3 is where we thoroughly validate the accounts. We have our readable picket from step 2, so now we check the credentials against it. We verify signer flags. Did the person who owns this account actually sign the transaction? We check writable permissions. Are we even allowed to modify this account's data? We ensure the correct account owners are in place. And finally, we convert the raw AccountInfo objects into domain-level structs. This step acts as a massive protective shield for your business logic. By the time the data leaves step 3, we have absolute certainty that every single account is valid, authorized, and formatted perfectly.
Now for step 4, the dispatch. This is where the bouncer finally unclips the velvet rope. We use Rust's powerful pattern matching on that enum we created in step 2, and we route those validated domain structs right into specialized handler modules. We are handing off the perfectly verified guest to the specific VIP room where the real business logic lives. And the beauty of this? The handler function doesn't have to waste time doing any security checks. It receives clean, validated data and can focus entirely on executing the core action, like minting a token or updating a piece of state.
The final piece of the pipeline, step 5, is mapping errors. Look, if the bartender, our business logic handler, encounters a problem, they don't go yell at the customer directly. They tell the bouncer, and the bouncer politely but firmly kicks the bad actor out. We catch the domain-specific errors returned by our handlers and convert them into stable, predictable program error custom codes that the Solana runtime understands. Keeping your error reporting centralized and totally deterministic at the entry point makes debugging an absolute breeze and ensures your program behaves exactly as expected on the blockchain.
And finally, section 4, shift change.
We've covered a tremendous amount of ground today, and this brilliantly illustrates our main architectural takeaways. We learned why we must keep the boundary thin. You want to be a strict dispatcher, not an overworked bartender. We learned to parse early, converting raw bytes right into typed Rust enums. We saw exactly why separating validation from business logic is just completely, absolutely crucial for security and clarity. And we learned the importance of documenting the contract expected by our handlers. When you build modular code following this 5-step velvet rope workflow, you drastically reduce your cognitive load, you eliminate messy monolithic bugs, and you literally slash your debugging time.
So before we wrap up, I want to leave you with a provocative question to chew on. If the entry point is just a clean modular pipeline with clearly defined inputs and outputs at every single step, how easily do you think we can test it? Well, the answer is incredibly easily. Because we've separated our concerns, we don't need a massive, complex, heavy environment to test out our logic.
And that serves as the perfect bridge to our next lesson, testing entry points locally. We are going to use these exact modular patterns we just learned to write incredibly fast, isolated unit tests, all without having to rely on a full network cluster. I want to sincerely thank you for joining me for this explainer today. As a quick reminder, this explainer was proudly made by Forge College. I highly encourage you to go visit forge.college to learn more about this subject, dive even deeper into smart contract development, and explore a whole bunch of other fascinating Web3 topics. Keep building, stay curious, and I'll see you in the next one.